in any typical machine learning activity, you have a bunch of numbers being given to the model, and then model does some combinations of mathematical activities like multiplications and additions, and then eventually you arrive at a final answer, and you want to do a back propagation to see, can I change the weight? So if x, y, and z are some sort of numbers or some sort of weights, and these could be arrays, and you do a multiplication of x and y, and you get an answer A, and A plus z comes out with B, and you do these activities over and over again, multiple times, and you have lots of answers B, and you summarize all the B's and arrive at an answer C, and then for, if you want to train a model, you actually have to go back in the same way to compute gradients for x, y, z based on the loss function. Loss function is, if C is the answer the model is giving, and if you know the right answer yourself, the difference between the right answer and the model predicted answer is called the loss, and you actually use that loss to compute the gradients, and the gradients are added or multiplied to your weights so that the weights are adjusted, so that next time when you give a similar data, the model actually makes a little more accurate prediction. And if you keep on doing this process for, let's say, 100,000 times or maybe a million times, model becomes more and more intelligent, and then it becomes eventually a good model where the accuracy rates are very high. Remind me if I don't tell you about this, the story about accuracy rates in models, because there is a very easy trick to get 99% accuracy in any model without doing anything, and I'll tell you the technique towards the end if you stay until 3:15. Okay, so this is a typical NumPy program where you've written a couple of lines, and I'm not going to explain each of it. So you create x, y, z as random numbers, and then you do the mathematics like a is equal to x times z, because that's what your computational graph is. The one on the right side is called computational graph. The term computational graph is extremely important when you guys work on machine learning models, because many frameworks depend on the concept of computational graph, because you create a graph and give it to the model, and that graph becomes some sort of a data structure for you, and then it runs extremely efficiently with lots and lots of data, especially if you have arrays. If you have a matrix, I've heard of matrix. If you have a two-dimensional matrix, it's fine, but if you have a three-dimensional matrix, sometimes even four-dimensional matrix, how do you actually have mathematics of that going? And every millisecond is multiplication going on, and in the back propagation, you actually have gradients, so you are adding those gradients to the original matrix, and then you repeat the process millions of times, and all the thing has to happen in a couple of hours in GPUs. And so anyway, this is what NumPy array looks like. This is import NumPy, and then you initialize the variables. This is the forward pass. So when you're doing a machine learning training, you give the data, and the model takes the data from left to right, that is from the start to the end in a forward pass. And once the model makes a prediction and you know the right answer, you do the backward propagation, and that's called compute the gradient. So you actually reverse back propagation is called computing gradients. And if you don't have a framework that's helping you to create the gradients, this is how you actually write it. You write your own. But again, this is a very extremely simple example I've taken. That is, I have x, y, and z, and then I'm doing a few mathematical operations on it. If it's a TensorFlow, it looks exactly similar too. For example, you have basic import. By the way, when you're using a TensorFlow, you always have to import NumPy, because it actually uses NumPy arrays. All the frameworks use NumPy arrays, but in TensorFlow, you actually have to explicitly import NumPy. If you guys allow me, I'm going to move my recording device more towards me. I'm going to post it on the YouTube eventually, maybe in a couple of weeks. Then you do the gradients. In the older version of, it's I think 0.9 or 0.12 of TensorFlow, even 1.0, this is how it used to be the executing the computation graph in TensorFlow is. So the fundamental concept in TensorFlow is you define a computational graph, and then you run the graph. When you're defining, even though you show program where, like in this step, even though you are telling the a is equal to x times y and b is equal to a plus z, the actual computations are not happening there because you are defining the graph. Whereas once you're done with the graph, then you run the graph. All the activities that happens after TF session is a special function. You're going to tell TensorFlow, okay, now start doing whatever I told you to do, and it starts doing. And till then, even though you have defined the variables and placeholders, you have not fed the real data into the model. So, you know what? I saw a couple of guys yawning. I'll tell you a story. This actually story is how to think out of the box, and this is you have to really pay attention to this question. This actually is a real story. In World War II, U.S. and British Air Force engineers were really worried about something because some of the airplanes going into the war zone, some they come back and some don't come back. And they want to make sure more number of airplanes come back. Yeah, makes sense? So they invited this famous professor and statistician called Abraham Ward. He's an Australian by birth, but he was in the university, I think, in somewhere in UK. He was asked, okay, find out how to get more of my airplanes back. He said, okay, fine. One idea was, let's put extra armor underneath the aircraft. Yeah, make sense? Yeah? No trick question, by the way. But the problem is, if you put extra armor, the carrier is going to be heavier, and then you have other problems coming in. So, put armor, but put as little as possible so that it doesn't gain extra weight, but at the same time it's really protected. So they said, okay, fine, interesting. Let's look at the aircraft, the number of bullets, the aircraft, the one coming back. So if you divide the aircraft into three major parts, the front big wings, if you say part one, and the tail two wings, the one is part two, and the entire body, like where the pilot is sitting, that body is called part three. They found very interesting feature that part one and two, that is the major wings and the minor wings, had more bullet holes than the main part three. Now the question is, where do you put the armor? Is it 1 or 2 or 3 or 1 and 2, 2 and 3 or 1, 2, 3?
Just 3.
Just 3, okay. You said 3 too, okay.
Are you looking only at the planes that came back?
Yeah, because you can't go to the war zone. Yeah, it's a different.
They're coming back. They didn't need armor. They came back. I would put it.
So you know nowhere.
I put it in the middle.
On the middle, so not part of the 3, okay.
I say 3.
So 3.
Pilot. I just want to send them in the war zone.
You want to sell in the war zone, okay. 1 and 2, okay. Okay, it's actually 3, number 3. So the story of the moral of the story is, looks like you guys are really paying attention. So I don't need to worry too much. I know a couple of guys joining, but that's energizing, getting more oxygen, I guess. Yeah. So TensorFlow, this is what I think you have a computational graph and you actually run that. So next time when you're developing a TensorFlow based model, you would have to think about how the graph is going to look like, or in other words, you would imagine or visualize the sequence of steps, the entire sequence of steps, how the model is going to take the data, compute, run, and do the backpropagation. And once you define that, that's a graph, and then you start running the graph by giving real data. Yeah.
You compute the graphs, TF gradient C, and in brackets X period Y period Z? Should it be commas?
Which?
Compute gradients.
Here?
Above, right there.
Mm-hmm.
X, Y, Z.
Mm-hmm.
Shouldn't it be X, comma, Y, comma, Z at the very last attribute, at the very end? Yeah, right there.
This is, first of all, yeah, again, I don't want to talk, I don't know the answer. Not a programming class, and also this is an older version of TensorFlow. It could be x dot y dot z or x comma y dot y comma z, but I think you sound more right, that x comma should be y comma z.
Sorry.
But again, I was not paying attention to that aspect of commas and periods. I was only paying attention to. Anyway, even for that matter, I think some of the brackets also were missing, but okay. Okay, so and the best part in TensorFlow is if you want to run the entire program using a CPU or using a GPU, it's just one flip of a single line of code. You don't actually have to write too much of code to run on a GPU. If you know the architecture of a CPU versus GPU, you would appreciate why this is so good, because typically CPUs don't have their own internal memory. They actually depend on the computers or the laptops or the desktops RAM or a storage disk, but GPUs actually have their own memory too. So what they do is when you run a model on using a GPU, if you have the entire data set on your hard disk, it actually loads either half or the entire part of it or the entire data set onto the GPU memory, because it becomes extremely fast if the entire data set is in the GPU memory itself. And right, that's first advantage. Second is CPU has around 8 threads or even 4 threads or 8 threads, sometimes 12 threads, but GPUs have hundreds of threads happening simultaneously. Especially they have lots of mathematical multiplications of arrays, especially 2-dimensional or 3-dimensional arrays. You actually can give different parts of your arrays, different parts of your matrices to different threads, and you can hugely parallelizes the whole activity. But the entire activity of CPU and GPU would make it, it's extremely simple by just having one single line of code. So that's why you do the GPU. In PITorch, the distinct difference between a TensorFlow and a PITorch is TensorFlow you actually have variables, then you have the computation graph in the variables, and you define all the mathematical equations there, and you start running a model. Whereas in PITorch, there is no one-time graph. Every time you run, that is every cycle you run a PITorch model, it's creating graph on the fly. The advantage of that is the code, when you as a programmer write, it's very easy to visualize and write it, because it's like any other programming you have been doing in your world. Whereas in TensorFlow, you got to define computational graph. Sometimes it becomes a little inconvenient because it's not the programming style. Until you get expertise into TensorFlow, it becomes a problem, because sometimes, even though you are writing a correct program in TensorFlow to compute the final answer, if all the dependent nodes are not being explicitly asked by you to run, if that some nodes it can miss, and it will still compute the final answer, but if it's not computing a specific node's mathematics, it will go ahead and compute without that node's input, and then you suddenly feel that your application is not working because TensorFlow's computation graph looks different. Whereas in PITorch, the graph is, it creates a graph every time you're running, so that's like a regular programming. Number one. Number two, it's the tensors being used and the modules being used, or the network layers being used in PITorch are relatively easy to grasp. So if you are into research, especially in the academic circles, if you're into research and writing, trying to invent or innovate new models, I think it would be a good idea for you to look PITorch. And this is how it works. So you have initializing the variables here. You do the forward pass. Again, conceptually, it's the same in everything. And then, so that's the forward pass here. And then if I have to take, if you want to use GPUs as opposed to CPUs, you just have to recast your variables as .CUDA as opposed to without the CUDA for GPU. Again, in other words, I think using GPUs in PITorch also is extremely easy. So if you look into a NumPy, all three lines of programs are computing the same activity. The picture, the graph I showed you, X, Y, Z and stuff, all are same. But the way TensorFlow does it and PITorch does is slightly different the way you write it. But the conceptual activity is very similar to what you see in NumPy. By the way, PITorch has NumPy embedded in it, so you don't import NumPy anymore. Whereas in TensorFlow, you got to import NumPy. This is an actual experiment of MNIST data. Have you heard of MNIST data? So if you want to run this, I think you should just scan this slide, and the next slide actually has the complete code. You can run it. For those people who have not of MNIST, is a data set of numbers 0 to 9 written in by human beings. They are obviously not in a perfect shape. The 1 and 2 and 3 numbers are not perfect shape. And if those pictures are fed into a model will understand using a deep learning approach, and then eventually figure out which image has 1 in it, which image has 2 in it. That experiment is called MNIST, or the data set is also called MNIST. And this entire program runs, so this is defining of the graph. So you have, you're identifying the number of nodes your model is going to have, number of classes. Here in this case, there are 10 digits, so the model has to predict one of the digits, that is 0, 1, 2 through 9, so there's 10 digits there. Then you're defining the neural network here, and if you're defining 3 different layers, if you look at layer 1, layer 2, layer 3, the architecture is extremely same, it's just the same. So for the first layer, it gets the inputs from the numbers, and the output of first layer becomes the inputs of the second layer, and the output of second layer becomes inputs of the third layer, and the third output of the third layer goes to the final layer, which is called output layer. You can call final layer 2, and then you would do something called ReLU, that is activation of these numbers, and then this is the whole graph you're defining to run. And again, you're installing TensorFlow and getting the data. Data is available for free online, and you don't need to. And it actually, the data comes with the TensorFlow. If you install TensorFlow, it actually has the data for MNIST also, so that you can run experiments. Define the number of nodes, define the placeholder, define a few layers in the graph, whatever number of layers. You can actually have 10 layers, 20 layers. It just takes more computation, more time. Again, the comparison between accuracy and number of layers, there's no mathematical equation. Just because you have hundreds of layers doesn't mean it automatically is higher accuracy. Okay, so this is again, you're defining the graph where how the prediction is going to, how you're going to do the prediction, then how you do the cost computations, and then how you're going to optimize it. Here is the actual backpropagation command you're calling. And then after that, you would run the whole graph with calling the TF session as ses, and then you would run it. And normally, in previous versions, you used to use a different command, but nowadays it's called ses run. TF global variables initializer, so where you're initializing all the variables you have defined in the graph, and then model starts picking up data. That's it. This 10 lines in this slide and another 15 lines, 20 lines in this slide together, I think maybe 25 lines would actually look at hundreds of thousands of numbers, handwritten numbers, and define some model which can easily start guessing what number you've given. And this is the Keras model I mentioned to you. Look at these 4 or 5 lines, this lines, stacked model. These 4 lines define what I showed you here. All of these lines put together with some minor modifications, of course, because this is TensorFlow and this is Keras, but that's how it becomes dramatically simple. So sometimes I feel if you write a Keras-based model versus a regular TensorFlow model, you may get code efficiency of 1:4, but if for every 4 lines in TensorFlow, you may just write only 1 line. Approximately, again, it all depends on what type of model you're defining. Keras is extremely simple. And also it helps you in experimentation. Even if you make a mistake, just go back and fix it. And learning is very easy. So here is the stacked model, and then you're defining the loss function, and then you're training the model. Training the model is so simple. There's no more graphs, computation graphs, and no more data. You just tell the model, model.fit is you telling the model, okay, go figure out how to train. And a huge amount of activity happens in the background. You would not even know, but you just have to tell the model, okay, now model.fit, you run the model with the right data and the number of epochs, that is the number of times you're going to look at the data and other stuff, and it starts training it for you. This is the tensor board I talked about. It does a real good visual display of how the model is training and various hyperparameters of your model, including your accuracy and stuff. Yes, sir?
You told us earlier how tensor is so popular, so useful, great. And then you told us Keras is way easier, so what's wrong with Keras?
Okay, nothing wrong with Keras. Now, if you are a... Hello? Your time is up. I don't know.
Google doesn't like Keras.
I'll try this off and on.
Is that a smart microphone?
There's nothing wrong in Keras. I don't know if someone can. Is anyone from here?
I think somebody went.
Oh, someone is coming? Okay. in my opinion, if you use a Keras, especially for your personal experience, experiments and stuff,
They're going for
okay, cool. For personal experiments and stuff, I think you can do it because a lot of fine tuning using your hyperparameters, like for example, learning rate, the batch size, there's so many other hyperparameters that goes into it. That type of fine-tuned settings are not there. There are some default settings, and you can actually go and modify it too, but that takes an extra effort, and hence, Keras is written more for an individual developer, for personal development, understanding of stuff. TensorFlow is actually an industrial level framework. So if you are a company developing a production-ready model, you would rather want to use a TensorFlow, which actually it's a little more down level, and you can code yourself at a hyperparameter level, and you can do fine-tuning better. At Keras, I don't think it's a production-ready system, but it is becoming so popular that they're adding more features so that Keras itself could be used at an industrial, at a production system. Number one. Number two, Keras actually use TensorFlow in the background anyway, so you will be using TensorFlow. In other words, you are making a higher level API calls to TensorFlow, which itself is actually making a bunch of API calls. For example, I mentioned backpropagation would have been extremely efficient if you had written the code yourself. But now, backpropagation is such a solved problem. It is really efficient using the default functions. But there are such functionality which you can still modify yourself. For example, a year ago, when PITorch was introduced, AutoGrad, as sort of an activation function, people were using their own written AutoGrad functions. So, in summary, what I'm trying to say is, if you're an individual developer trying to learn machine learning, developing your small-scale solutions, Keras would be extremely good. At least with the current days Keras, maybe in 6 months later from now, 1 year later from now, it really becomes production ready. But right now, between the two, I would go with TensorFlow for production ready stuffs. Okay, let's say a typical graph in PITorch looks this, again, is not much, but the district.
Thank you.
Okay, the differences between PITorch and TensorFlow, you know, I was holding it this way, I remembered Pavlovian experience, you know. Have you heard of Pavlov's experiments? Yeah, I was behaving like that dog. Pavlov's dog, yeah. Anyway, so PITorch and TensorFlow, they're very, very similar, even though they have slightly different concepts, but in terms of the structure is similar, except, as I mentioned to you, computational graph is static graph in TensorFlow. That is, once you define it, that's it. You can't do any more changes. But the advantage of that is it really runs very efficiently. But the disadvantage is if you want to make any changes while computation is happening, based on certain conditions, you cannot do static graphs. PITorch allows dynamic graph. It is easier to program because that looks like every other program you would have written, and hence it's easy to write. And also it's efficient when you have any multiple paths of graph you need to take. For example, if a value of A is greater than this, take this route, but a value of A is less than this, take a different route. That type of computation changes in the graph cannot be done in TensorFlow, it can be done in PITorch. Okay. Many times if you just hit it against the wall, it works, but I didn't want to do that. So again, if an example using a PITorch for a similar, again, the graph which I showed you earlier, for that you still again define the data sets here, then you do a forward pass, again, very few lines of code, and then here backward pass. The backward pass in this example, we are doing computation because remember I showed you an irregular graph of x, y, and z, and then multiplications and additions, and that's why you're doing a backward pass. But if you have a little more regular process, you would have used an automatic backward pass. And here you're updating your gradients. Okay, so again here in PITorch 2, to run it on a CPU versus GPU, it's just a flip of a line of code. See, there's hardly any change between this and this. You just have to say CPU or GPU. You have to cast it differently. Actually, I made a mistake there. It's torch. For the CPU, it's torch.float tensor.
and if it's GPU, is torch.cuda.floatTensor. Sorry for that, that's a typo for a GPU. Okay, here is the last slide, actually about my suggestions. If you are looking for any recommendations in terms of what framework should I focus on, these are the recommendations. Again, none of these companies paid me, so TensorFlow I would use by default for any activity you're developing. If you're in a learner mode, you can use scikit-learn and Keras, yes. But you could use TensorFlow, because the advantage of using TensorFlow, initially it may be a little difficult, but eventually when you become more and more an expert and start migrating from CPUs to GPUs, you would actually have a same consistent framework being used. Otherwise you got to learn scikit-learn first and Keras once, and then you'll go to something else. You can avoid that. Also, TensorFlow I think would have a long life going forward, because it's been supported by a company called Google. Yeah. And then of course, Keras would be another good framework I think if you want to use, because it actually is a wrapper on top of TensorFlow, but that's for your personal understanding and thing. PITorch is extremely efficient. It's becoming stable now. Torch was more stable, but PITorch is relatively recent. It's getting stable now. But if you're into academics, and if you're doing research papers, you should use PITorch. TensorFlow and Caffe used a lot in industry. Caffe too for image processing models, because they also have Model Zoo, because they actually have pre-trained models available. Now TensorFlow also has a few, but Caffe too introduced the concept, and they are more popular for Model Zoo. TensorFlow and Caffe too is also used for mobile devices, and if you're using Spark in your organization, use Spark ML Lib as your framework, which would help you. Now comes your reinforcement learning frameworks. If you have not heard of reinforcement learning, please do read up a little bit about that. There's this I think is one of the introductory blogs. There's a link at the bottom of the slide. You can look at that up later. How reinforcement learning is used. And if you're not familiar with the reinforcement learning, I can give an example. You want an example?
Yeah.
If all other models until now I spoke about, you have to have a supervised learning, or maybe unsupervised too, but when I say supervised or unsupervised, you need to have lots of data, and then the data should have the right answers identified already. That's called supervised. Sometimes you don't have the right data, then you can do a clustering sort of activity which is unsupervised, but predominantly you know what the right thing is in those data sets. But imagine you are developing an AI model to play chess, and imagine two grandmasters playing chess with each other. Yeah? Grandmasters are extremely talented guys or girls who know chess in and out. And individually, both of them are extremely good in the game. But eventually, one wins and one loses, right? The losing GM, Grandmaster, is not any less talented. But the sequence of steps the losing GM took was the wrong sequence. Yeah, in the context, of course, of the winning GM. If you want to develop an AI model where for every step you don't know whether it's the right thing to do or not, but eventually you know that's the right thing to do. So that's a chess example. Let's say you're driving autonomous cars. You start from your home and reach work, and if you've been driving, if you're a regular driver to work, many times, I don't know whether you realized, you would reach office, and then without even realizing that you were driving on those roads, without even checking whether you ran a red light or not, you would have been perfectly following the traffic rules, but you just never paid attention. So, every step you may be taking the right step, but you may get into an accident because of so many other situations too. So in other words, if you want to do an autonomous cars, you have to tell the car after a series of steps whether you did this entire series of steps, were they correct or not. So there's no answer, right or wrong answer for every step, but for a collection of steps, you need to, a right or wrong answer. In that context, if you're training a model, the concept or approach being used is called reinforcement learning. So you actually reinforce the right thing or the wrong thing by giving a reward to the model, telling the model, okay, this was the right thing to do, this 10 sequence of activities, or these 10 or 15 sequence were the wrong sequence, but the 10 sequence were the right sequence. So you give a reward. That's called reinforcement learning. It's being used for autonomous cars, even robots. For example,
You might have seen Boston Robotics video, I think, well, if you're not seeing it, you should have seen it. It's a human-looking robot. It's picking up a box and moving it, and then the researcher is pushing it down, pushing the box down, pushing the robot down, and then still robot is waking up and doing the right thing. And in that type of trainings, you have to use reinforcement learning. You cannot do anything other than that, because there's a sequence of steps that the model has to do, and then be told, okay, this was the right sequence or not. Yeah.
So the difference between the supervised learning and this is what? Even in supervised learning, data point is you know that it is a right or wrong. In this, it's a sequence of steps versus one data right or wrong. Is that what is the
That is one difference for sure. In a supervised learning, for every data point you're giving it into the model, the model says, okay, I understood, but I understood in this way, and they say, no, that's right or wrong. And then you do a backpropagation and then update it. And then you do repeat that thousands of times, millions of times. In a reinforcement learning, you give a multiple inputs, multiple steps, and then you tell the model that this is the right thing or not. Second is the difference between this and supervised learning is sometimes you may even not have the right data. For example, for autonomous cars today, if you are a company developing autonomous cars, let's say it's Google or Waymo or Google, I was saying, let's say Mercedes-Benz or BMW, you can't be having hundreds of hours driving on the street and then using that. You can still do that, provided you'll only get the right driving. But if you want the wrong information about the wrong driving, you got to actually hit people in the cars, right? And you can't do that. So, and model, you will never be able to tell the model what's the wrong thing. You'll tell me what's the right thing. And hence, the other difference in RL is you actually are generating the sequence of right sequences, wrong sequences, and the technique for that is the generative adversarial GANs I talked about, generative adversarial networks that's being used, and a bunch of other things too. But for today's session, I would say instead of giving feedback to the model at every step, you give the feedback at the end of a few steps, and that's what reinforcement learning is.
Thanks.
Sure. Of course, TensorFlow has their own RL framework. It's called TensorFlow Agents. It's really a good one. Of course, there is another one called RLlib. Developed by UC Berkeley. Again, all of these frameworks are very, very recent. I have not worked on it. By the way, I didn't mention at the start of it my personal bias about the frameworks. I have worked on scikit-learn, TensorFlow, a little bit on Caffe, worked on Torch, never on PITorch, never used MaxNet, CNTK, all those frameworks. I've used only, as I said, TensorFlow, scikit-learn, a little bit of Caffe, a little bit of Torch. Again, based on my own interaction, based on what I've read on the internet, and also my interaction with my fellow developers and their sorrows, then I could feel this is my opinions about good frameworks.
So regarding the robot navigation, for example, you mentioned the reinforcement learning. Do you know how it compares to like a simple A-star search or something like that, which is actually taking really steps every step of the way, as compared to making a decision after so many steps? I wonder what your thoughts are on how they compare you as experimented with that.
Yeah. Giving a feedback at every step is not possible for every type of use case you're trying to solve, and hence reinforcement learning took birth. Otherwise, if you know what is the right thing for every step, then you can stick with reinforcement learning. So autonomous cars also you can still drive. For example, if you are driving on a 4-lane road, and there's no traffic on the first 3 lanes, 4th lane there is a car, and after some time, on the 2nd lane, let's say from the right, there is an object lying on the road. Now, if you say, keep on lane 1 and you drive for X number of hours, no problem for you, and then that could be a supervised learning, where you can just say, keep driving, there's nothing on the street, keep on driving. But there are so many unknown scenarios. Like I said, in autonomous driving, you don't know what all things is going on. 8 months ago, there were models developed for autonomous cars where you have multiple cameras in the front and it's actually taking pictures and figuring out what is on the car. There is a very famous model that was invented 2017 June, so 8 months ago. a model called YOLO, Y-O-L-O. Have you heard of YOLO? Yeah. So this is called you only look once, not the other one. You only look once. So this model actually takes a picture of what's happening in front of it and then tell you what does it see. The first YOLO had 24 frames per second, FPS. That is, it can process 24 frames in second. It would be good, let's say, if you have that on your phone or on your camera here on your shirt, you're walking around or on your glasses, it'll fine. But let's say you're driving a car, you would actually need a lot faster because in 1 second you would be actually crossing, let's say, I don't know, 50 meters or 100 meters or whatever. YOLO 2 came out, I think, December of 2017. It does 220 frames per second. Slightly lesser efficient because they had to really cut down the size of the model so that it runs faster. But accuracy is still high, but dramatically faster in terms of efficiency. That, they actually, you can go onto the YouTube and check some of the implementation. They have the YouTube videos where you put it in a car, you're driving it, it actually shows on its screen all the trees and the people and the cars. It sees, it immediately identifies. So that's the first step in an autonomous car, because if the car knows what is in front of me, then you have to put the regular intelligence. Okay, if I see a car, do the following. If I see a human being, do the following, all that stuff. But those unknown situations, because of so many unknown situations and scenarios, you can't actually have data for that. And hence reinforcement learning came. Okay, for this series of steps, this is the right thing or the wrong thing. Maybe we will eventually come to a stage where we'll have enough data to say, okay, if there is a car here, you are on the first lane, and there is another car changing lanes, and there is a big object lying on the street, do this. Second scenario, you're going on this 3 lanes, but another car coming. So there's so many scenarios, infinite scenarios. If you have data for that, maybe you can use supervised learning.
No, I was thinking more of the game of chess, right? Because in the game of chess, you could give feedback after every step. And how does that compare to giving feedback after the whole sequence of steps? Because you have a finite set of possibilities there.
Yeah, good point, yeah.
That's kind of what I had in mind.
Let me give you an example of a chess game, and also, let's say, image processing model where you're giving processing images of cats and dogs, let's say. So you're processing 1,000 cats and 1,000 dogs, and you're giving a picture. The model looks at the cat picture and says, oh, this is an elephant. They said, no, this is not an elephant, this is a cat. So it's like, oh, okay, I'll change it. And give another cat with a different, when I say same cat, it's not the same looking cat. It'll be a picture taken from this angle, or just this angle, or maybe a different color cat, different size cat, or cat doing different things, sitting, running, jumping, or whatever. So it's not the same picture. So for every picture, you can tell the model very specifically, you know what, this is the feedback, and yes or no. Whereas in a chess, let's say, as I mentioned to you, 2 grandmasters playing. Remember, every step they really think through and they play. So every step they are taking is extremely valuable right step. There's not a wrong step. Only the sequence of 10, 20, 25 steps they take in the context of what the opponent is playing, then eventually they'll lose. For example, I don't know, my son is a chess player, and I was reading up a little bit, and I never played chess with him because it's a bad idea to play with him. Because then he'll have more opportunities to make fun of me. There was a study done. I think for regular people who don't play chess often, they were shown an incomplete chess board with a few of those pieces on the board. And they showed, I think, 30 such boards, different looking boards, in a span of, I think, 1 per second or 1 per 5 seconds, I think. And then they asked regular people who don't normally play chess to recollect each board and the position of each token, each piece. Human being, regular guys, regular people could just not even do 1 board. Grandmasters could recollect 15 to 20 boards, all of the tokens. And the reason for that is they don't remember individual pieces. They actually remember relative positions of various items in it. And even when they play chess, they actually, when they look at it, they're looking at various patterns. So in other words, you might have seen in some of the movies, like you see Sherlock Holmes, for example, if you've seen it on Netflix, when he sees the director of the show wants us to see the same item. So what they do is they blur the all other items. They just only show one item clearly, which to show Sherlock was observing that. That's exactly what they do. When they look at it, if they want to see certain pattern, they only see that pattern, and then they look for other pattern. Anyway, the point is that no step is a wrong step they take. Eventually, they are forced to lose because they don't have any other better way of doing it. That's why they lose, and hence there's no feedback on every step to be done. Okay, so.
Yeah, but no, but your probability space is actually quite smaller compared to a self-driving car for sure. But no, I agree with you from that point of view. Yeah, I see it. Thank you.
Just you mentioned your bias. So we used for the Kaggle competition this year, identifying the nucleus in cell images. We ran it on PITorch on the Google Cloud with a UNet implementation that's straight out of a research paper that just came out like weeks ago. That took us about an hour and a half or so to run, cost 72 cents. But on our actual work, one of the leading health management companies wanted to develop a model for identifying radiology images and diagnose them preliminarily so they could prioritize it. That was going to be a TensorFlow implementation all the way. That's for a more corporate setting. That's
Yeah, you're right. I think what I said was, TensorFlow in a corporate setting for production-ready systems. Cafe2 for image processing production systems, and if it's a research paper doing experimentation, because even writing code in PITorch is easier, and also I think it's a lot more stable. Now it's stable, of course, relatively stable, but it's a lot more easy to do research projects there. Yeah. There are other machine learning frameworks too. For example, the surprising element is the Intel's Nirvana coach. Intel Nirvana was a third-party acquisition. It's supposed to have a good ML framework. It is not as popular as compared to the other ones, but I have not used RL framework from Intel Nirvana, but this will be a good, interesting study. I think you will see more evaluation of these individual frameworks going forward too, and I'll be using it too for our. We're working on an autonomous car project too ourselves, so we are actually working on trying to do RL. There's another one, Robo School. Again, I've not worked on this, but that's my last slide for the frameworks, and that's my last slide.
Can we go back 2 slides?
This one?
One more. Thank you. That's it.
Okay, so that's pretty much what I wanted to share. Yeah, I still have 10 minutes. We can stop. You would have by now figured out that I like to talk, and it's a good idea. I think you guys should tell me, okay, now it's time to stop. But yes.
What's Digitalist do?
Digitalist, again, she's asked the question. I'm not saying it myself. Yeah. We are a customer experience design company, and also we are an AI company developing products, and we also do consulting for customers on AI solutions. With that segue, I'll tell you a very exciting area of research happening in AI world. If you should see this more research coming out of it. Image processing, like video processing, is being used, let's say, in healthcare scenarios, on surveillance and security scenarios. People can do it, right? You would have heard of that. Even though that research itself is so relatively recent, in the last year and a half. But there's one problem in using videos for processing or creating machine learning models, and that is privacy. You don't want people taking pictures there. Number two, what if it's dark? Let's say you want to do a patient monitoring or a baby monitoring, but if it's dark and the model cannot work efficiently because it's a video. Third is, it's called line of sight. If the camera can see what's happening, then it can make sense. What if someone is behind the door? So our latest research, actually I was speaking on a conference on Tuesday, 2 days ago in San Francisco, on how to use Wi-Fi signals to detect human activity and using machine learning and deep learning. So in 6 months from now, you would see lots of indoor areas, whether it's a house or a hospital or a stadium or an airport or a railway station, everywhere. You would see, if there are, of course they would reveal it, they're not doing sneaky, but routers could be used to track human activities in terms of walking, sitting, falling, breathing, talking, keyboard. There's a research paper done where I was sharing about the research results too. It actually can track which key in your keyboard were you striking. and it can figure out exactly. So it could be used for surveillance too, but they did not do any more research on the actual use case. They're actually using it in an experimental lab situation. Anyway, that's last set of information.
You said you were going to share a technique for like 99%.
Oh yes, yes. So there's a term called accuracy in models, and typically, let's say you want to predict how many people are going to buy my car or whatever. I think the accuracy rates are very high, and even in fraud detection too. I think if you have lots of transactions, which one is fraud, which one is not fraud. The accuracy can be 99% is, let's say the answer is yes or no, let's say. There are two classes. In machine learning terminology, it's called classes. You have two classes. But if you have data, 99% of the data supports one class and only 1% of the data supports one other class, which happens typically in your fraud detection scenarios. There, unless you have that 1% data augmented by some other method, model will become so unintelligent to figure out what is the right answer. So 99% of the time, it may say yes, even though it's not a yes, it's a no thing. So if that is the scenario, you don't need to even use the model. You can just say it's 99%. Every time it's right. And you're still 99% accurate because the data or the use cases you're seeing is 99%. But again, it's more of a joke thing. It's not really, because you don't want to use that. In a fraud detection situation, you can't say, you cannot use that model because banks are really working on identifying even those minute number of cases of fraud, and you just can't say yes for everything. Yes. I can't hear you.
So we spent a lot of time on Python frameworks. Is there any thoughts on something like DL4J or?
I don't know about that, the DL4J. I've not used it myself. I know other languages like even C, C++ are being used for certain frameworks. Even for example, Cafe, in the background they actually have lots of C being used, so C, C++ is being used. There is a Kaggle research done, published report, I don't have it in my slides, but I was presenting at a different conference. Python seems to be unusually high popular among all machine learning experts. So I would rather, I only use Python, I don't use any other languages. I've used a long time ago, but not anymore for AI. If I have to make a recommendation, I would also say Python, and hence all my focus is on Python thing. I'm sure there must be other, but I don't know. I don't know the frameworks.
Come back to the dark side.
Yes, sir.
All the tools that you mentioned today are available as R packages as well, with the exception of scikit-learn, but the Carrot package.
I guess so. I guess so. Thank you. Yeah.
So if I had a company and I wanted to get started with a machine learning framework, so how would that look like from an operational point of view, like infrastructure? Is it usually like you have like a couple servers and then you run your models on those, or you have like, is it like hosted infrastructure, or what would you recommend?
If you're developing the model, you can just borrow servers on the cloud and then do the development, the training and testing, or do it internally also. That is once you do the model. If you want to put it in the production, then you got to look into your current infrastructure, where is your rest of the systems are. But if you don't have any other system, if it's a startup company, you don't have any other legacy of infrastructure, then you can go to Google Cloud or AWS and host it there. Typically, if you're using TensorFlow, you may gravitate towards GCP, Google Cloud service, because it seems to be easy, because they also have some free service where they even do consulting, free consulting, because they're using their services, and hence TensorFlow. But if you use AWS and if you have a problem with TensorFlow, you may not find enough experts there because they don't have much of it. That except like a few friends of my friends work in Google, they do have high-profile customers and are taking TensorFlow and also doing that in Google Cloud. They actually have a big, massive professional services team who are trained in TensorFlow. So you may have that extra access to intelligence to if you are stuck in developing a model. Except that I think for developing the model, you can do it anywhere, and then when you productionize it, you can put it anywhere.
In general, can you compare GCP and AWS?
No, I think both are really good. Both are really good. The video is recording.
I know.
My wife works for Google, so I don't want to. When I go home, I have to get my food and dinner.
Could you put the last slide up? Check your information.
Okay. Yeah.
Your last one.
The one here.
circle one. Oh, okay. I thought no, you didn't care for that. Okay, thank you. Yeah. You want previous one too?
Yeah. Thank you.
Okay, so ladies and gentlemen, thank you very much. Appreciate it. Yeah.